When writing programs, it is common to repeat a section of code, but not immediately after.
Therefore, it is more complex than placing the code once as the body of a loop.
Typically, the code becomes a functional behavior we want to repeat, and once we have developed and tested it, it is natural to reuse it.
Code reuse is central to many aspects of good practices in software engineering.
Assembly language illustrates some techniques to achieve a primitive level of code reuse.
MIPS illustrates early code reuse under the notion of macros.
A macro marks one or more places where a code section will be inserted before the entire program is translated and placed in memory for execution.
For example, suppose we want to issue a system call to output an end-of-line character after we print a string.
Such a macro would replace the standard 3 instructions that set the system call with just one line.
We may be more generic and create a behavior to output a string.
Such genericity can be achieved at the level of macros using parameters.
The code of programs becomes more readable, because we have created a way to abstract 3 instructions into one.
Our MIPS language has been extended with an output statement for strings.
The extension is not safe, because the macro has side effects.
It changes the values of register $0 and register $V0 from their status before the macro to values set in the macro.
Although macros are used extensively in many aspects of software development, in particular, configuration management, they are not an ideal solution because the code is longer.
The notion of subroutine is a way to abstract the behavior and encapsulate the instructions that achieve the effect so that later we can invoke it as many times as necessary.
Thus, we would like that calling the behavior results in control jumping to the start of the behavior.
When the behavior finishes, the control returns to the caller's next instruction.
We may implement this idea with the unconditional branch of assembly language.
However, the first difficulty is that if we use the subroutine repeatedly, the address of where to come back will be different.
The address where the subroutine starts is fixed, but not where it returns.
A second challenge is that the subroutine would take control of everything, at least at the assembly language level, and may change values in many registers the calling behavior wishes to preserve.
That is, we call a subroutine to do some specific behavior, like compute the dot product of 2 vectors, but not to alter some other values that could disrupt the work of the caller.
We want the subroutine to be an abstraction, and get the sense that someone else is doing the work somewhere else, does not touch what we're doing, but completes a subtask and gives the requested result.
Moreover, this idea of procedural abstraction is so powerful that when developing a subroutine, it is useful if the subroutine has its own subroutines.
For instance, to arrange the numbers in an array in descending order. It may be easy to find the largest value and place it at the front of the array.
We repeat finding the maximum but only for the array less the first item.
We continue with an array with a size of 1 element less.
All good, except that we need to write the code to find and place the largest in the first position of the array.
If the array is of length 1, only one value is the largest.
If the array is of length 2 or longer, we can call ourselves as a subroutine with the array of all elements but the first, and complete our job by just comparing the first element in the array with the largest element in the tail of the array.
That way, we place at the front the largest.
When we call subroutines that call subroutines, they become nested in a way that one subroutine is not finished until its subroutines are finished.
The return addresses, which we know are not constant, and the context of the caller, cannot be stored in only one place but in a sequence where the last item in the data structure must be the first to come out.
A sequence with such behavior is called a LIFO abstract data type, but is also commonly known as a stack.
All programming languages that use what is known as blocking calls use a stack to record the place where control should return once the callee is finished, as well as the parameters and local variables.
MIPS provides support for a runtime stack and instructions for jumping into a subroutine and jumping out of a subroutine.